In the previous video, we talked about graph isomorphism and what it means for two graphs to be isomorphic. And we saw that if you can define an isomorphism from one graph to another, then that means they're isomorphic. But what if they're not isomorphic? Clearly, you couldn't define an isomorphism, but to say that there is no isomorphism without proof would be insufficient. So how can you prove or verify that two graphs are not isomorphic? We're going to use what we will call graph invariants. And these graph invariants that we're going to define are order, size, degree sequence, and identify a given substructure. So a numerical graph invariant, or simply a graph invariant, is a property or a number that is invariant under isomorphism. So the most obvious of that would be the total number of vertices. Certainly, if two graphs are isomorphic, then they would have to have the same number of vertices. So the number of vertices is a graph invariant. This is usually referred to as the order of the graph. The size of a graph is the number of edges. And clearly, the size of a graph is also a graph invariant. So a theorem, if G and H are isomorphic graphs, then the number of vertices would have to be the same, and the number of edges would have to be the same. That is, they have to have the same order and the same size. Theorem 2.4.3 states that if F is a graph isomorphism and V is a vertex in the graph G, then its image in H, f of V, must have the same degree as V. So another way to think of it is vertices have to map to vertices of the same degree. Since this is true for every vertex, we have corollary 2.4.4. The degree sequence is a graph invariant. Now recall that we were wanting to find a way to verify that two graphs are not isomorphic. And if we can find just one graph invariant where they differ, then they're not isomorphic. So let's look at the saturated hydrocarbons that we had for a homework assignment. In the homework assignment, we had to give two different drawings of saturated hydrocarbon with 4 atoms, or 4 carbon atoms. And in our lecture, we saw 2 different drawings of a saturated hydrocarbon with 5 carbons, which is what we have on this page. And it was intuitively clear that these are 2 different molecules. But now, looking at them as graphs, let's talk about their graph invariants. They both have 17 vertices, so they have the same order. They both have 16 edges, so they're the same size. Furthermore, they have 1, 2, 3, 4, 5 vertices that are each of degree 4, and all the remaining vertices are of degree 1, so they have the same degree sequence. So it's clear that two graphs that are not isomorphic can have a large number of graph invariants that are the same. We need to find just one graph invariant where they're different. Theorem 2.4.5 in our book states that the isomorphic image of a graph walk is a walk of the same length. In other words, a walk in a graph, which is a sequence of vertices, would have to produce the same sequence in the isomorphic image. How this results is it gives us a corollary that's very useful. So returning to our saturated hydrocarbons, let's look at the hydrocarbon up in the top left. If we start to the far left, we can find a path of length 6. You move vertex by vertex, 1, 2, 3, 4, 5, 6, going right down the middle. Now let's look at the other saturated hydrocarbon and start it on the far left and try to trace out a path of length 6 like we just did in the preceding example. We can begin and go 1, 2, 3, and then we reach that fork. If we go up, then 4 and 5 is the longest path. If we go straight, again it's 4 and 5. And I think it's fairly easy to convince you that the longest path in the saturated hydrocarbon on the right is 5, but the saturated hydrocarbon in the upper left is 6. So they have a different identifiable substructure. The one on the left has a path of length 6 as a subgraph, and the one on the right does not. For our next example, let's look at these two graphs. The graph on top has 3 4 cycles. The small one on the left, the big one on the right, and the 4 cycle that's generated in the middle by the connecting 2 lines between the small and the big one. The graph on the bottom, if you'll notice, we have changed one of the adjacencies. We still have the 4 cycle on the left and the 4 cycle on the right, but we no longer have the 4 cycle in the middle. And in fact, by changing that adjacency, we now have generated a 5 cycle. So we could say these are not isomorphic because the bottom one has a 5 cycle and the top one does not. Or we could say the top one has 3 4 cycles and the bottom one does not. Our final theorem is theorem 2.4.9, in which we learn that 2 graphs are isomorphic if and only if their edge complements are isomorphic. This theorem can be helpful because sometimes it's easier to see why 2 graphs are not isomorphic if we look at their complements and see that their complements are not isomorphic. So we have discussed graph invariants and how we can use these graph invariants to verify that 2 graphs are not isomorphic. The number of vertices, or the order, the number of edges, which is the size, the degree sequence, possible subgraphs, and the number of those subgraphs, and the edge complement. So a graph invariant is a number that is invariant under graph isomorphism. What this means is if we have a different graph invariant for 2 graphs, then they are certainly not isomorphic. The invariants that we've talked about here order, size, degree, sequence, and substructures is just a small sampling of the large number of graph invariants.